Perfect. Yeah, so thank you very much for the opportunity to speak at this great workshop. So as Lance said, the topic of this talk will be a little bit distinct from the main theme of this workshop, and it'll be trying to understand a particular class of observables, which are called energy correlators, which try and measure or characterize the asymptotic flux of energy in collider experiments, for example, involving QCD. And so a lot of what I'll talk about in this talk will be progress on trying to understand these from a perturbative perspective. But part of the bigger motivation in trying to understand these observables and characterize them precisely in quantum field theory is so that we can ultimately try and make contact with non-perturbative approaches, for example, those discussed in this program, because ultimately if one wants to understand real-world QCD, you need to have some techniques for understanding non-perturbative gauge theories. Okay, so as everyone here is certainly aware, non-perturbative techniques have been extremely successful for describing certain classes of observables in quantum field theory. And so this has been primarily the lattice, but recently there's been a number of developments of other numerical techniques. And so most famously, these have allowed, for example, for the calculation of the spectrum of hadrons in QCD and other QCD-like theories. And they've also enabled the calculation of multi-particle scattering amplitudes below multi-particle thresholds. So this picture is a bit confusing, but it's the three-particle scattering of 3 pions to 3 pions. And this can be computed in real-world QCD. And so this is extremely impressive. But there's another class of observables, or kind of another regime of QCD, which one might like to try and understand. And so that's the regime of kind of high-energy colliders, where you are above multi-particle thresholds and you can produce kind of many, many particles coming out. And so this is, first of all, it's interesting because this is what we can actually do in colliders, but it's also interesting for trying to understand the dynamics of confinement. So in addition to just trying to measure the spectrum, one would actually like to understand how quarks and gluons, or perturbative quarks and gluons, confine into the hadrons that we ultimately see in the detector. And so the only way of doing this is to go to sufficiently high energies where you actually produce these asymptotically free quarks and gluons, and then look at the distribution of hadrons which come out. And so for this perspective, this type of observable, which is quite distinct from multi-particle scattering, is a very interesting thing to try and both study experimentally and understand from first principles quantum field theory. And an additional motivation for trying to understand these observables is that this is what we actually do to try and study the standard model. And so being able to understand QCD precisely in these high multiplicity collisions is very important just for our ability to, for example, search for new physics or better understand many aspects of the standard model. And so the full non-perturbative simulation of these extremely complicated multi-particle events is too hard and arguably not exactly what one would like to do. And so instead, what one would like to try and do is to target specific physical observables where you can really relate what you would measure in an experiment to certain precise properties of the underlying field theory. And so one of the simplest observables one can try and target are correlation functions of energy flow. And so this is just like if you try and study some conformal field theory, you start by building up the 1-point function, 2-point function, etc. And so for studying collider physics, what one would like to try and do is to also measure correlation functions in the energy flux. And so this is this average null energy operator, which you can think of as kind of a calorimeter cell, which just measures the expectation value of the energy in some particular direction n. And so to try and characterize the energy flux in some collider, you can try and measure multi-point correlation functions of this particular operator. So for example, the simplest thing you can do is to measure the 1-point function. So this just measures kind of the direction of energy flux in your collider, and then you can try and measure 2-point functions or higher. And so the reason why this is an appealing approach is that these observables are directly measurable by experimentalists, but you can actually relate what you're measuring in the asymptotic energy flux to properties of the underlying theory. So for example, these 2-point correlation functions of these energy flow operators can be obtained as certain limits of the 4-point function of 2 stress tensors. And so this relates what you're actually trying to measure in a collider to a very sharp question about the underlying field theory, which then if you had non-perturbative techniques to, for example, compute this object, you could actually make predictions about what you see in collider physics experiments. And so before going on, I should say, so this is not a new idea, and in particular this was introduced actually 50 years ago this year, when it was shown that you could compute these objects in perturbation theory, and then just after that, or where the kind of 1-point function was introduced and shown that you could compute in perturbation theory, And then shortly after that, multi-particle correlations were introduced and computed in perturbation theory. But one of the things which has really changed is there's been kind of a rejuvenation in interest. You can see there is almost no citations of this paper for a kind of 20-year period. And so what I want to kind of explain in this talk is probably why there's been this resurgence of interest in these particular classes of observables. And so this will both be due to progress on the theory side, but also really due to the availability of data which has come out in the last year, which really allows us to study these observables with extreme precision, and I think will teach us many interesting things about both perturbative and non-perturbative aspects of QCD. And so as I said, what I want to describe in this talk is some of the recent progress in really kind of connecting theory and experiment across a wide range of collider experiments. And so these observables, which are kind of directly related to theory, have actually been measured in a whole variety of experiments, all kind of within the last year. So surprisingly, these actually hadn't been measured in hadron colliders. And so they've been measured now very precisely in E plus E minus colliders at extremely high energies in proton-proton collisions at the LHC, and also in very complicated collisions involving large nuclei, which I won't talk about here. And so what I want to do is kind of go through a little bit the physics of what's being probed in these simpler collisions, and show why this is kind of very interesting for understanding aspects of QCD, and point out some places where non-perturbative techniques could be helpful for trying to better understand these observables. Okay, so the first thing I want to do is just go through the absolute simplest setup of trying to understand these observables in E plus E minus colliders. So as I said, this is conceptually the simplest case to study, because in this case, you're really producing your state with a local operator, in particular the electromagnetic current. And so what you'd really like to understand is just this 4-point function. And so as I'll try and show you, already this object is actually remarkably rich in QCD, and is sensitive to many aspects, both perturbative and non-perturbative, of the theory. And so this observable has been computed quite accurately in perturbative QCD, as well as in n equals 4 superhuman mills, and so there's been a lot of studies about its perturbative structure. And so the other aspect which makes it very exciting, as I said, is that this can be directly measured in E plus E minus collisions, and so it's a very nice opportunity for an interplay between theory and experiment, because it's really just this very simple observable which you can try and understand. So since this observable may be unfamiliar to people, I just want to give people a little bit of an intuition for kind of what this looks like and what aspects of the theory it's actually probing. And so before showing it in full real-world QCD, I just wanted to show how this observable behaves in two different toy theories. And so remember, what we're trying to understand is the correlation in energy flux as a function of the angle between the two detectors in your theory. And so always plotted in terms of this variable z, which is 1 minus cos of sine of the angle over 2. And so when z is 0, it means the two detectors are very close together, or in what is called the collinear limits. And when z is 1, it means they're back-to-back. And so the simplest theory where you can understand the behavior of these correlators is just if you have some source which has, for example, if it's like a scalar to some very high power, which is a form factor producing many particles in some uniform distribution. And so if you just have some uniform distribution of energy in like a free theory, what you get for this distribution is just a flat line, as you would expect. And so the same will be true in some strongly coupled theory if you're just producing kind of a uniform mush, which is coming out. So before going to QCD, we can next understand the case of just a weakly coupled conformal gauge theory. And so already in this case, this 2-point function actually has quite an interesting behavior. And so I won't go into all the details of it. I'm happy to discuss it afterwards. But it has these kind of two regimes. So in this weakly coupled conformal gauge theory, it takes this form of this green shape here. And so it has kind of two regimes, each of which is dominated by specific operators in the theory. So in this small angle limit, it exhibits a power law behavior, as you can see here. And so it has, which is kind of physical because you have essentially correlations at arbitrarily small angular scales. And this is governed by what is referred to as the light ray operator product expansion. And so in particular, it has a power law with some particular known exponent, which you can compute in the theory. And so for people that are familiar, it's the twist 2, spin 3 anomalous dimension. And so this just gives a very nice power law behavior at small angles. In the other limit, when these detectors are back-to-back, it's governed by the physics of Wilson lines, so very high spin physics. And in particular, there's kind of a closed form expression for this in terms of the so-called cusp anomalous dimension, which governs essentially the dynamics of Wilson lines. So you can already see that this very simple observable kind of sweeps out and probes the physics, both of these kind of low spin operators in your theory, as well as Wilson lines. And so now what we'd like to understand is what happens when you add confinement into your theory. And so essentially what will happen when you add confinement, which is shown in this red line here, is at some scale, QCD just confines and it goes into hadrons, which are non-interacting. And you can think of these as essentially being uniformly distributed. And so at some particular scale, this nice power law, which you had in the conformal gauge theory, just breaks and you transition to a very flat behavior. And so this really gives kind of a very clear signal of the imprint of confinement into the structure of these observables. And so it's kind of a nice target for trying to understand and how confinement really imprints itself in the asymptotic energy flux. And so one can then go out, and of course these are measured very early on in data, and try and look for this behavior. And so these are measurements, so these are actually the first measurements of this observable in the 1980s compared with very early calculations, as well as more recent measurements from LEP. And you can see that these do not kind of manifest all the nice behavior which I was showing you. And so this is either true because these are very low energies where you don't kind of see this asymptotically free regime of QCD, or because if you really want to study the details of the confinement transition, you really need to measure these things at extremely small angular scales where confinement actually imprints itself. And so, for example, if you look at this, you can't see these nice kind of scaling associated with uniform hadrons coming off into your detector. And so motivated by this and the kind of recent theory developments, we wanted to actually go back and try and really precisely measure this two-point function so that we could kind of both see all these nice behaviors and to have a kind of very clear target for improving our theoretical calculations. And so in collaboration with an experimental group at MIT, who is an excellent group of experimentalists led by Yanji Li, what we actually did was try and go back to use the old data coming from the Aleph experiment and to kind of reanalyze this using modern techniques so that we can apply these to study energy correlators in a very, very nice form. And so I won't go into all the details, but I'll just highlight kind of a fun fact about this is that the QCD LEP1 data set is 28 gigabytes. So you can actually put this on, or you can put this on a thumb drive that you can buy for like $8. So it's a really very simple data set. But you can actually analyze it using kind of modern experimental techniques. And also we now have much better ways of performing the theory calculations. And so I'm not going to go into all the details of this. But the kind of upshot of this is one can perform kind of very, very nice measurements by reanalyzing this data. And so if you actually go out, and so this is, these experimentals did this, and so this is an actual plot of the real experimental data, so now done in a very kind of precise angular scale, and you can really see all these asymptotic regimes of QCD, which I explained earlier. And so this is very satisfying that we can really see the kind of different scaling behaviors associated with either this light ray operator product expansion or the Wilson line, and you can really see these transitions to really over orders of magnitude having this perfectly flat scaling associated with just kind of free hadrons, as well as the sharp transition between this kind of scaling regime of asymptotically free QCD and just hadrons. And so you can really kind of very accurately see these hadronization or the confinement transition. And so we can also now use kind of modern techniques to calculate this observable very precisely. And so it's a little bit hard to see on this projector, but you can see our calculation in the gray shown here. And so you can see that overall we get a very good description of this observable. And so I'll just kind of highlight some of the different regions. So this is a kind of log plot, so it's very hard to actually see how good it is. And so let's go through a couple of these different regions and showing how well we're actually able to describe it, and some of the regions where we could hope to have some improvement. Okay, so first in this perturbative region where we can just use perturbative QCD. So this is something where we now have very good control over this. So we can compute these. We have kind of anomalous dimensions which describe the scaling behavior to like 4-loop order. And so this can be achieved very precisely. And so again, this is not for kind of this audience, but one can compute in the kind of central region where it's really perturbative QCD at the level of a few % accuracy. And so one can really use kind of state-of-the-art QCD techniques to compute this extremely, extremely precisely in this perturbative regime. And so you can see things start to break down as one goes to either the kind of non-perturbative regime on either side. So on one side, we actually have pretty good control over this observable. So in this back-to-back limit, as I said, it's dominated by the physics of Wilson lines. And so this is something where there's been a lot of progress in non-perturbative techniques on the lattice to actually extract the anomalous dimensions controlling the structure of these Wilson loops. And so this is something which goes in the name of Collins-Soper kernel. And so what we can actually do is we're able to compute to high enough orders, so we can compute this to 4 loops in perturbative QCD, and we can actually match, it's a bit hard to see this here, but for this particular anomalous dimension which describes these, we can actually match onto lattice data, so unfortunately the perturbative QCD is kind of covered, but we can actually match onto lattice data, which allows us to extend this out deep into the non-perturbative regime. And so this is really an observable where we're starting to be able to compute it to high enough orders in perturbation theory, where we can actually start having a match with these very nice lattice calculations which have come out recently. So that's very satisfying. On the other side, so this is zoomed in and with a slightly different Jacobian, but showing this very small angle limit, where as I said before, you really have this imprint of confinement going from this nice scaling behavior to a kind of behavior of just non-interacting hadrons. And so this is something where we have absolutely no control of how to compute it. There's no known way to do it on the lattice, and we just lose perturbative control. And so this is something where it would really be beneficial to try and have some real-time approaches to compute this observable non-perturbatively. And so for us right now, we just have this kind of gap where you have this rearrangement of degrees of freedom from quarks to hadrons, or quarks and gluons to hadrons, and we have no way of calculating it, but we're able to measure it quite precisely. And so in my mind, this observable, which we now measured extremely precisely, is a very nice target for trying to compute non-perturbatively using some of these real-time numerical methods that are being developed. So even just in 2+1D, I think this is a very interesting observable to try and compute. And so for example, this is not my work, but just to highlight it, so there's been some recent attempts to compute these energy correlator observables using quantum computing approaches. And so this is definitely not the be-all and end-all, and so of course these are extremely small, and so one can question whether one is actually measuring kind of asymptotic fluxes, and also you have a very discrete choice of angles, so you can't really measure these things very much as a function of angle if you only have a few cells, but it's at least interesting as an attempt to try and show how you could compute these observables non-perturbatively, and I think this is, now that we have this extremely good QCD data, it's really kind of a target for lattice or non-perturbative techniques to try and understand how to compute this class of observable. Okay, so now I'm going to switch gears a little bit. So that was the kind of simplest case of E plus E minus, where I think there's a very nice case to be made for trying to mesh with non-perturbative techniques. And now I wanted to show a little bit about how very high energy colliders allow us to kind of really study these observables in a very nice regime where we really just have very clean perturbation theory. And so this will just be more highlighting a little bit how one can really take advantage of the high energies to just see beautiful perturbative behavior of these correlators in a kind of different regime of QCD. So this transition from these low energy colliders to even more extreme regimes where you have very, very high multiplicity production allows us to really study an even higher energy regime of QCD, really in the asymptotically free limit. And so what we're going to try and do in this talk is so in the case of E plus E minus, one can really measure these things as a function of angle. But here we'll focus just on this collinear limit, where I described in the E plus E minus case, we just have this nice scaling behavior. And this is sometimes referred to as the jet substructure limit. And so we'll try and see what we can do by measuring these correlators inside very high energy jets at the LHC. And so the simplest thing we can do is to look for a form of scaling behavior. So as I said before, at very small angles, the behavior of the energy flux is governed by what is referred to as the light ray operator product expansion. Again, the details of this don't exactly matter, but what it says is if you measure the multi-point or the two-point correlation function at very high energies, much above lambda QCD, as you bring the two detectors together, they should exhibit a particular angular scaling in the energy flux. And so these are set by particular operators in your underlying theory. And so at very high energies, you really just get access to these observables in the perturbative regime. And so it just gives you access to the spectrum of operators which appear in this operator product expansion. And so if you go out and do this, because you can go to extremely high energies, so for example, this is 2 TeV, so these are extremely, extremely high energy jets at the LHC. And so you really have access to QCD in this multi-TeV regime. And so you can see this is just a plot of this 2-point correlation function shown here. And you can see that it exhibits this essentially perfect power law scaling behavior at these very high energies. And so this is very nice because it's really an experimental realization of this detector operator product expansion. And you can really see this kind of new regime of QCD where you get this beautiful scaling behavior. And so it's kind of fun to compare this measurement done at 2 TeV with this original measurement which I showed you here. And so in particular to compare the kind of scales of the measurement or of the angular scale at which you're probing things. And so if you look here, this is in theta, this is like 10 to the minus 3 or 10 to the minus 2 as compared to the kind of entire plot shown here. And so you're really essentially blowing up this entire kind of little bin shown here, and you're getting this huge kind of new view of the behavior of QCD in this kind of asymptotically free regime. And so this is really part of what has generated a lot of the recent excitement about these energy correlators, is that you can really, for the first time, get access to this very nice asymptotically free regime of QCD where you can do these nice perturbative calculations. Okay, so one thing which you can do, which is even more nice, is that you can, just like moments of the structure functions, you can actually measure higher point correlation functions. And so each of these has a different anomalous dimension, which depends on the number of points in the correlator. So just for experts, so kind of J point or a J minus 1 point correlator, you probe the twist 2 spin J operator. And so one thing which is very nice about this is you can take ratios of higher point correlators to the 2-point correlator, and you essentially isolate the anomalous scaling, and you can just read off the spectrum of anomalous dimensions of these particular operators shown here. And so this is something which can actually be directly done in experiment. And so this is a measurement of this 3-point correlator normalized to this 2-point correlator. And so it should go like this particular difference of anomalous dimensions. And so in the free theory, this would be flat, but you really just directly get access to this nice scaling behavior. You can really see that at these extremely high energies, you just get these perfect scaling behaviors, as shown here, which allow you to really kind of access this very nice scaling behavior. And this is something which is kind of unimaginable in these low energy experiments. And so one actually has such good control of the scaling behavior that you can really use this to extract the value actually of the strong coupling constant. So you can perturbatively compute these anomalous dimensions. And you can actually extract the value of the strong coupling constant at a few % accuracy. And so this is now kind of one of the best ways of doing this using these jet substructure techniques. And our hope is that by kind of taking advantage of this kind of nice theoretical way of doing this, we'll actually be able to get, for example, optimistically kind of 1% measurements of the strong coupling constant. And so this is something which can be considerably improved, and I'll probably skip a little bit how that can be done, and try and go on to describing a little bit higher point correlation functions in energy flux. So obviously the simplest thing one can do is just to measure these scaling properties, but one thing which is really neat about the LHC is you can actually measure higher point correlation functions inside jets. And so why would you want to do this? So this should be something which is very familiar, for example, from studying the cosmic microwave background. So there's been tremendous progress in trying to understand the structure of cosmological correlators. And so higher point correlation functions allow you to, for example, distinguish different models of inflation. And so one would like to understand what is the structure of kind of higher point functions of energy flux, for example, at the LHC. And so one of the reasons from a theoretical perspective why you might want to try and do this is that these higher point correlation functions provide a kind of playground for exploring the perturbative structure of physical observables in quantum field theory. And so these are just observables you can actually go out and measure. And so as compared to scattering amplitudes, one can hope that to make contact with, for example, strong coupling or integrability type approaches. And so they're kind of a nice playground where we can use a lot of the techniques of modern scattering amplitudes or integration, but directly at the level of physical observables. And so I won't go into too much detail, but there's kind of 2 approaches to doing this. So one is by computing correlation functions of the stress tensor itself, and the other is by performing perturbative phase space integrals using squared form factors. And for these higher point correlators, it's really been the second approach which has been extremely successful. And so one of the things that is very nice about these observables is they exhibit a very elegant structure in this collinear limit, which is what you can actually measure inside high energy jets at the LHC. And so if you try and compute them, what you get is a structure of an integral which looks almost like a Feynman parameter integral. So it's some integral over a kind of canonical simplex like this, multiplied by what is referred to as a universal splitting function. And so this is a very nice class of integral which one can try and explore in perturbative gauge theories quite generally, just for understanding the structure of squared amplitudes, as well as for extending techniques for studying Feynman integrals to this slightly more general class of integrals. And so for a time, I'll skip a little bit the technical details and just jump to some of the answers just to show that these can actually be computed and measured. And so we computed both the 3 and the 4-point correlation function, and I'll show them just in n equals 4, but they can also be computed in real-world QCD. We found that they actually took a kind of very simple form. And the thing which is very nice about this is that this is actually the observable which you measure in your detector. So you really just have some nice function which you can compute, and it's exactly what you measure in your detector. So you can go out and measure, for example, 3-point correlation functions of energy flux. And these are a bit harder to read. Up in this corner is kind of an equilateral triangle. Down here are these squeezed triangles, and here are this flattened triangle, just like you measure in cosmology. But you can really kind of measure these higher point correlation functions and directly compare with what you compute. And so it's a very nice that you can kind of directly compute these physical observables and measure them in your detector. And just for even more fun, I'll show the result of the 4-point correlation function shown here. And so you can see what's been done here is you fix 3 of these correlators, and then you can kind of move this around. And so you can actually measure at these experiments multi-point correlation functions and really kind of play with them. And they have a beautiful perturbative structure, which is only possible in these very high energy experiments. And so this is something which was completely impossible a while ago and really gives you access to this very exciting regime of QCD. And so these higher point correlators are very important for enabling many new strategies for searching for new physics or performing precision standard model measurements at colliders. And so in addition to trying to actually achieve these, it will be very important to try and understand the non-perturbative structure of these observables. And so that's again where the ability to try and simulate these observables using some first principles or strongly coupled approaches would be extremely important. And so just to conclude, so in the last couple of years, there's been a huge amount of progress in trying to understand energy flux observables in quantum field theories in general and QCD in particular. So we're now able to very precisely measure the scaling and shape dependence of multi-point correlation functions, or these energy correlators, at both E plus E minus colliders and at the very high energies of the LHC. And the hope is that progress in numerical techniques will allow us to really understand some of the more non-perturbative aspects of these collider observables, or at the very least that we've now kind of very precisely cornered some of these non-perturbative effects, and so that it gives a very clear target for these numerical techniques. So thank you.
Thank you very much, Ian, for this tour of energy correlators at colliders. Are there some questions?
So, well, suppose you raise the energy of your collider and you hit a new particle. So typically, how you discover it is that when you subtract the background, you plot the cross-section, you have a bump.
Yeah.
So in the framework of energy correlators, how it will show up?
Good. So it depends exactly how it decays. But so one example, and so that depends on the number of correlators that you would have to measure. But so an example of exactly this case is, for example, if you produce some top quark. So you go to high enough energies that you produce a top quark. So this has a predominantly 3-body decay. And so what you can do is to measure the 3-point correlator in that case. And then what you get is a peak at the angular scale associated with the decay. And so the same would also be true for like a Higgs that is primarily a 2-body decay. And so if you measure the 2-point correlator, you see some peak in the distribution at an angle which is just like the mass of that particle over the energy. And so you can think of this as just all these examples that I showed of these nice scaling behaviors are in the conformal, or you can think of them as kind of being in the conformal case, and anytime you insert a scale, you'll just get some bump or some feature at that scale. And so that's similar to the confinement case. You're just seeing the imprint of that scale, and so essentially anytime you put in a scale, you just see it as some kind of bump or feature. The particular shape depends on the nature of that decay, but you'll always just see it as some imprint at that physical scale.
Sorry, Steve. Steve has a question back here. A couple of questions, so we'll take two in a row back here.
Thanks for a fantastic talk. You showed what happens due to hadronization in the plus E minus case.
Yeah.
How does that go in the multi-point correlators that you showed at the end?
Good. So that's, less understood. So that's partly why these have only been, so these I showed, or these multi-point correlators, I showed at extremely high energies, where we're to first approximation neglecting that. And so I should say we only really understand, so for the case of E plus E minus, we actually understand, relatively well how to at least write down like matrix element definitions of the non-perturbative corrections. So we understand quite well how to write down matrix element corrections for the leading non-perturbative corrections for this. And they have a simple enough, so essentially what happens is they're coming from some soft limits. So what you have to compute is some kind of non-perturbative or kind of an expectation value of the energy flux in some Wilson line type background. And in the particular case of the two-point correlator, these Wilson lines are back to back, and you have essentially a boost symmetry which fully fixes the result up to one number. And so then that's kind of under control. In these and you can extract it from experiments. In the multi-point correlator case, now you have multiple directions, and you can in principle write down like a non-perturbative matrix element that characterizes this, but it's no longer, it now depends on multiple variables. And so this object is just, first of all, it's not known, and it's a much more complicated object. And so the only case where we really have any control is in the two-particle case. And so for the other ones, that's why we've always just pushed to very high energies. But yeah, that's a great question.
Nice talk. So actually, this slide is what I wanted to ask about. So right around where it kind of turns over in the middle, it looks like it's power law on the left and power law on the right, and kind of approximately the same.
Yeah,
power law,
yeah.
Is it exactly the same? And kind of, can you remind me of the physics that goes into this?
Yeah, so it is actually not, so one of the things that's a bit misleading about this plot is it's like double log, so it's very hard to tell what's actually going on. So they both are modifications of, so at like zero or at lowest order in the coupling, they're very similar. But this one really has a power law like this. So this one is really a strict power law, at least in the conformal case. In the non-conformal case, there's some beta function corrections. But here you really have like a 1 over z power law with some very slight modification. Here you have this double logarithmic result coming from Wilson lines. And so again, it behaves, so on this side it behaves like 1 over z. This side it behaves like log 1 minus z over 1 minus z. And so that's why in this region, if you're kind of ignoring higher order, the resummation, they look pretty similar. You can't see by eye like a log over, but then the actual structure of the higher order corrections is quite different on the two sides. And so one is really this double logarithmic series governed by the cusp and Wilson lines, and then this is governed by like low spin, twist 2 and almost dimensions, or like collinear physics. So one is really kind of collinear physics, and one is soft or Wilson line physics. Oh yeah. So it's a bit hard. So it's a bit hard to see in these plots because it's very, very zoomed out. But if you like actually go into this, again, these are all, the problem is that you have to zoom into specific regions. But yeah, you can very clearly resolve that. Yeah.
By the way, even though they're very different, there's actually a weird sum rule that connects the two, right?
Yes.
If you integrate
Yes.
with z and integrate with 1 minus z, you have to get the same answer. But of course, the detailed z distribution has very different physics going on.
Yes, absolutely.
This may be asking for too much, but is there any case where this would help find new physics? I mean, for example, if there were new soft physics in the TeV region, can you see a place where this might give a nice handle on that, or is this beyond the
No,
reach?
I think it's an interesting question, which people have not investigated, to be honest, too much, and I think it should be thought about more clearly. And so they're a bit different than, like, so a lot of the approaches to look for new physics are to kind of tag for some unusual feature. And so these are more ensemble, so you just measure some distribution and have to look for something which modifies that distribution. And so one thing which is actually, so for example, these plots of the scaling shown here. So these are measuring, or these are kind of probing the physics at the energy, so like let's say 2 TeV, times the angle. And so as you measure through here, you're really kind of sweeping through your theory from like 2 TeV to a few GeV. And so if you had something which modified the physics of your either the anomalous dimensions or was just inside the jet, you would see it as some modification of the slope in here. But people have not really looked precisely in this form. But it is implicit in the fact that this agrees with QCD is implicitly showing there's nothing too crazy there.
Yeah, but I mean, when you have a new particle that goes off at wide angle, then of course you see it. That's great.
Yeah.
But I mean, the question, if there's new soft physics, maybe this would be some kind of global way to see that something's going on?
Yeah. And so I think depending on the particular nature of the physics, that could definitely imprint, for example, in these, or something that's just like inside the radiation or just modifying the structure of the radiation, you would see it in these. And so they haven't really been, like, let's say, recast in terms of putting limits on specific models. But the fact that this agrees is implicitly showing there's nothing too crazy going on. But it's interesting to investigate specific models for sure, and I think people will certainly do that.
Yeah, thanks for a great talk. I think we discussed this a couple years ago, but there are confined backgrounds in gauge gravity duality that exhibit this transition from conformal to confining behavior. And I was wondering if anyone has tried to calculate these energy.
So some people, I didn't show it, I should have. There's been some work by Csaba Csaky's group in trying to use, I didn't show it.
Just some hard wall?
So just like a hard wall. But one of the, and so they exhibit some of the features which one would expect, but not all of them. And so one of the problems that makes it difficult is you really need some form of string breaking. In particular, in this collinear, you need some kind of regime where it's really so to get this nice, to really get this shape of the transition, you need a regime where on this side, you're really kind of able to very freely break the string or to really have asymptotic freedom, and then you need to turn over. Otherwise, you just produce something which just kind of bounces and sits there. And so this is, I think, the problem with some of these approaches is you really need both features. Otherwise, because the problem is if you're really in something which is strongly coupled and then it confines, what happens is actually very similar. So,
but to get string breaking, you need basically finite n, like you're saying. You can't deal with infinite n.
Exactly. And so one of the problems, when I showed here, so in this like back-to-back limit where it's probing soft physics, it's already flat perturbatively. And so therefore, if you confine in that region, it just stays flat, and you actually don't see the confinement. And so one of the problems with some of these models is if you're already kind of strongly coupled and uniform, and then you confine, you just don't see, it's just kind of going from between two different types of uniform distribution. And so it's like it doesn't really imprint in the right way into the correlators. And so what you really need is this region where you really just, are freely kind of breaking things, and you get the scaling and then some transition. And that's much harder to realize in these models. It'd be very nice if there's some, even if it's a little bit artificial, it'd be very nice because the bar is, essentially 0. But it's much, much harder because of that feature. So you can definitely do it in some of these hardware models. You get something, but it's not this.
Well, maybe one needs to add brains that allow for fundamental dynamic.
And I think this should be explored more. And I mean, their group is trying this a little bit, but I think it should be explored more because even trying to get some qualitative understanding or constraints on this behavior would be very, very interesting. And because one can compare it with real world data, so just any expectations for the behavior in that region would be great.
Thanks a lot.
Yeah.
Of course, there are also non-field theoretic models or string confinement in Monte Carlos.
Yes.
Like in the case where you mentioned you could extract one parameter from experiment.
Yes.
You could probably also check that it comes out from Monte Carlo correctly.
Yes. So it works relatively well in Monte Carlo.
It's been tuned up to similar
and it's been,
data.
But also even trying to compute these things in like some effective string model, I mean, this would be interesting to try and understand more analytically what is going into these simulation or these Monte Carlo simulations. I think that would definitely be a direction which would be good.
Any more questions? Can you go to slide 18, taking my... So here you showed the Alice data against Is this the straight collinear two-point function?
Yes.
It seems to lie, at least down here, somewhat above the data, whereas I know in the Aleph case it was kind of on the other side.
Yeah.
Do you understand what's going on there?
This one has a different normalization. And so this one, because it's in the hadron collider case, it's been normalized in a particular region. Okay. And so this one is much less precise.
The normalization isn't really...
this one should not look at... It's also lower energies. And so this one should not read as precisely. It's just that they made this plot that's kind of zoomed into this region where you can nicely see this transition, but it should not be taken with, also the calculations done at much lower orders, and so this one should not be taken too seriously.
Any further questions? If not, let's thank Ian again.